Okay, so welcome to Math 310, Introduction to Algebra. This is lecture 10. So what we're going to do today is we're going to see some applications of group theory. We're going to be doing RSA, and then we'll move into a new topic. We'll be doing rings. So we'll be talking about definitions, examples, and properties. Yes?
But I'm really confused.
Just 1 second. Let me hit pause. Okay, so what we're going to do today is we're going to start off by doing RSA. We're going to talk about some applications of the stuff that we're doing. So we ended the last lecture with Fermat's little theorem. So you might have heard of Fermat's last theorem. The x to the n plus y to the n equals z to the n has no solutions in the integers if n is greater than or equal to 3, unless you do something stupid like choosing one of x or y or z to be 0, in which case it's really not that hard to solve y to the n equals z to the n. Right? Fermat's little theorem is that if a is relatively prime to n, then a raised to the phi of n equals 1. Oh, so sorry. This was the. I gotta, oops. Get rid of the dot. Okay. So we have the dot. Okay. So it's typically not that hard to find a number that's relatively prime to n. And then phi of n is the Euler-Toshin function, which we talked about, is the number of integers from 1 to n that are relatively prime to n. And if we take any number relatively prime to n and raise it to phi of n, we always get 1. And one of the really nice applications was if n equals a prime p, then phi of p is p minus 1. And that implies a to the p minus 1 is congruent to 1 mod p. So we could actually use this to do a partial primality test. If I give you a number a that I think might be, if I give you a number n that I think might be prime, I find a number relatively prime to n, and I raise that number to p to the n minus 1. And if I don't get back 1, it's composite. And we use this to prove that the number 6 is composite. The problem is if we actually want to do this in practice, the numbers that we need to test for primality are going to have on the order of 200, 400 digits. We cannot do a times a times a times a 10 to the 400 times. That's just way beyond anything we have a chance of doing. Earlier in the semester, we talked about how many subatomic doohickey whatchamacallit thingamajigs are there in the universe. If each one of these was a universe running since the dawn of time as a supercomputer, we're not even close to being able to do something like this. So if I wanted to calculate a to the 100, how many multiplications to get a to the 100? So how many multiplications would it cost to calculate a to the 100? Oh, 100. Almost. Nope. You went the wrong direction. 99, right? It's 99, right? How many multiplications does it cost to get a squared? 1. A cubed would then be 2. A to the 4th would be 3. So to calculate a to the 100, that's 99 multiplications. To calculate a to the 10 to the 400, that's 10 to the 400 multiplications. Now, we saw earlier in the semester when we looked at the Euclidean algorithm that initially the Euclidean algorithm could have taken a long time to run. If every iteration we only decreased by 1, this could take 10 to the 400 steps. But every 2 iterations, the remainder decreased by at least a factor of 2. And that greatly accelerated it. So rather than taking on the order of 10 to the 200, it took log 10 to the 200. Log 10 to the 200 we can do. That's less than 1,000. We can do 1,000 operations. There's something similar. So we need what's called fast multiplication or exponentiation. And this is one of the most useful tricks in mathematics. What's x times x? X squared. X squared times x squared. X to the 4th. X to the 4th times x to the 4th. X to the 8th. X to the 8th. X to the 8th. X to the 16. X to the 16. X to the 16 is x to the 32. X to the 32 x to the 32 is x to the 64. And I can stop here, because if I give you a number like 100, I can write 100 in binary. So I want to write 100 in its base 2 expansion in terms of powers of 2. What's the largest power of 2 that's at most 100? To the 6th or 64. In fact, that's why I've got the 2, 4, 8, 16, right? So 100 is 64 plus 36. What's the largest power of 2 at most 36? 32. So it's going to be 32 plus 4. Oh, great. We're already done at this point. So 100 is 64 plus 32 plus 4. So if I want to calculate x to the 100, that's x to the 64, x to the 32, x to the 4. So all I would have to do is multiply x to the 64, x to the 32, and x to the 4. So the number of steps that's needed is much, much less than you would expect. If you want to count, to get to x to the 64, I've got to do x squared is 1 multiplication, x to the 4th is 2, x to the 8th is 3, x to the 16th is 4, x to the 32 is 5, x to the 64 is 6. 6 multiplications to get x to the 64. I multiply by x to the 32, that's 7. I multiply by x to the 4th, that's 8. So the cost is 8 multiplications. That's a tremendous savings. The worst case would have been if I had to do everything. So what would be a worse number than 100? What's the worst number I could do for us in terms of the most multiplications? A number around 100 that's going to require more multiplications. Which numbers did I not include when I multiplied to get 100?
90.
Look at the numbers here. Which numbers did I not use? I used x to the 64. I used x to the 32. What did I not use? 16, 8, and 2. And in fact, I could also have x to the 1 as well. What do you think the worst numbers that is around 100 would be for us? If you put in 16, if you put in 8, if you put in 2, if you put in 1, what number do you think you'd get to? 127, 1 less than 128, right? Right? So if you're 1 less than a power of 2, that's going to be a lot of multiplications. There's a trick you can do. Anybody know what you could do if I gave you x to 127? Well, but x to the 126 is going to be expensive. So if I want to get x to the 127, I don't want to have to multiply everything.
X to 128.
I mean, could you do like x to 64 times x to 64 and then like times x to the negative?
Yeah. Basically, you overshoot, you calculate x to the 128, and then you fall back by doing a division. So depending on where you are, it might actually be easier to overshoot and calculate x to the 128 and then do a little division. So when you're looking at this, the question is, how expensive is this going to be in general? Most of you are probably not going to be group theorists, later in life. But you might have to use technology, and it's important to know how long is it going to take to do things. If we have to do 10 to the 400 operations, it's hopeless. There is no chance of this being of practical use. So the question is, how do you see the relationship between 8 and 100? Well, if I'm looking at powers of 2, x times x is x squared times x squared is x to the 4th, and I keep going down. Let's say x to the 2 to the k minus 1 times x to the 2 to the k minus 1 would be x to the 2 to the k. And so I want 2 to the k to be roughly the size of n. Right? So that means I need k to be roughly of size the log of n base 2, or if you really like the natural log of n over the natural log of 2. That shows you that this fast exponentiation is really cheap. You know, if n equals 10 to the 200, then k is on the order of the log base 2 of 10 to the 200, which is 200 log base 2 of 10. Anybody know what the log base 2 of 10 is roughly? An upper bound for it, maybe?
Around 5.
Upper bound 5. You can do a little bit better than 5. Because 2 to the 5th is 32. So you can do a little bit better than 5. What's a power of 2 that's less than 10? I mean, that's greater than 10. 2 to the 5th is 2. Well, 2 to the 3rd is 8.
2/3, yeah.
2 to the 4th, right? So this is going to be less than or equal to 200, the log base 2 of 16, which is 4. That's less than 800. We can do 800 steps. And every time we do this, we're often going to be doing this on a clock with n hours. So we're going to be constantly reducing things. The numbers are never going to get that large. The worst case for us would be we go all the way down and then we have to multiply everything and come all the way back up. And so the cost, worst case, the cost is approximately 2 times the log of n base 2, because we might need to include everything. Are there any computer science people here? Okay. What kind of computers do you use? Give me their specs.
Oh,
Okay. Okay. How fast is the processor? Okay. Disk storage?
It's got 500 gigabytes.
500 gigabytes.
Yes.
Okay, so you didn't get the model with infinite disk storage. No, okay. So one of the problems when we're looking at this is keeping track of all the things that we need, right? So you might actually worry a little bit about disk storage. And so this is, small, but, if the number is huge, maybe there's a little bit more things to store. Now, in anything we're doing, the number of things that we're going to have to store is negligible, so it doesn't really matter. But I'll just end with a quick trick to show you how to handle some of the stuff like this. So we want to calculate x to the 100, which is x to the 64, x to the 32, x to the 4. And so we know we are going to need x to the 4, we're going to need x to the 32, we're going to need x to the 64. So let's start off with the pair x comma 1. From this, we can calculate x squared. And I'm going to keep the 1. And then x squared times x squared is x to the 4th. And now I'm going to change the second component and put an x to the 4th there, because x to the 4th was one of the factors I needed. X to the 4th times x to the 4th is x to the 8th, but x to the 8th doesn't occur in my expansion, so I'm not going to change the second component. X to the 8th times x to the 8th is x to the 16. X to the 16th doesn't occur, so I'm going to keep this as x to the 4th. X to the 32, I do need that, so I'm going to keep this now. I'm going to multiply x to the 4th by x to the 32 and get x to the 36th. And then the last one, x to the 64, and I multiply that. So we only ever store 2 items. So rather than having to keep track of everything and then do all the multiplication at the end, I can just keep the second component free as a storage facility and then just keep updating that as I go along. So again, a lot of times you are not going to be noticing any of this happening. And a lot of you, there's a reason you don't know exactly what your computer does and what its specs are, because it's fast enough for everything you need to do. You don't have to worry about doing anything too efficiently. I am old, okay? I am so old that my dad splurged when I was young. He bought me the 16 kilobyte RAM extension for the home computer we had. So I had 16 kilobytes of RAM. I wrote some beautiful programs to do chaos and to do fractals and zoom in. And if you just evaluate polynomials naively, it was too slow to evaluate. How many of you know Horner's algorithm? So we are going to be talking about polynomial evaluation in rings, and so this becomes a nice way to segue into that. The big theme for today is just because you can do something one way does not mean that's the way you should do it. Sometimes, sure. If you have processing power that's extremely efficient, you don't have to worry about these things, don't worry about it. But if you are doing something many, many times, if any small little change matters, then you need to think about how can I optimize things? How can I do things quickly? When you're doing anything in terms of security, you want to be working with primes, you want to be working with numbers that are large enough that you don't worry about people cracking them. A lot of the original guesses that people had for how secure certain systems would be completely failed. Your computers got better a lot faster than people were expecting, and certain levels of security did not provide the security for as long as people thought. So just because things can't be done now doesn't mean somebody can't do it better later. And so here we had Fermat's little theorem. Beautiful, beautiful theoretical theorem. And why do we care about something like Fermat's little theorem? One was primality testing. And another one is, for this to be useful, we have to be able to multiply numbers quickly. How many of you have done linear algebra? Every hand should be up. How many of you have done any numerical methods to compute eigenvalues? Or did you just use the characteristic polynomial? Yeah, no one uses the characteristic polynomial in the real world. Yeah, you're not going to be doing this with a 10,000 by 10,000 matrix. So you need to find an efficient way. Now, theoretically, as a mathematician, you say, and you write down the characteristic polynomial and you solve it. Well, we can't even solve a polynomial of degree 5. If you give me a polynomial of degree 10,000, you need some techniques. And so you guys are getting deep in your career in math. It's worth pausing for a moment and think, can we actually use this stuff? I just wrote, oh yeah, just raise it to the phi of n. Well, if phi of n is of size 10 to the 400, can I actually do this calculation in a reasonable amount of time? And if I didn't have fast exponentiation, the answer would be no. So this is the difference between just a pure math result and actually using it in the real world. So I will end with Horner's algorithm. And this is one of my favorite algorithms in all of mathematics. Let's say I give you a polynomial f of x is 7x to the 4th minus 13x cubed plus 11x squared minus 8x plus 12. If I wanted to evaluate this polynomial at 2, is this a hard problem to evaluate this function at 2? So how many multiplications would this cost? So how many multiplications does it cost to evaluate this? How many additions? And of course, subtraction is the same as addition. So how many additions are there? Let's do the easy one first. 4. How many multiplications? How many multiplications does it take to get the first term? 4. And the second? 3, 2, 1, 0. 4 plus 3 plus 2 plus 1 plus 0 is 10. More generally, if I give you f of x is, a d x to the d plus a d minus 1 x to the d minus 1 all the way down to a 0, the number of multiplications is d plus dot 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 plus 1 plus 0 is d plus 1 over 2. Number of additions is d. If you think about it, addition is much cheaper than multiplication. So the reason addition is much cheaper than multiplication is if I give you two numbers to add, you basically just add vertically, right? Addition is cheap. So if we have two d-digit digit numbers on the order of D operations. So imagine I have two binary strings of length D. And if I want to add them, it's basically going to be D simple adds of 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. Okay, maybe I have to carry, so maybe it's going to be of size 2D. But it's going to be linear in D. It's going to be linear in the number of digits. Multiplication is expensive. If I have 2D digit numbers, it's on the order of D squared. Because I have my first digit times the whole digit number, the second digit times the whole digit number, the third digit times the whole digit number. So multiplication is going to be of size D squared. If D is large, D squared dwarfs D. Okay. If I tell you that you owe me $1,000 for coming late to class today, are you happy? We have a couple of people who are late. Are you happy if I tell you you owe me $1,000 for coming to class late? What if I tell you, but for those of you who came in late, I'm going to give you $1,000 squared dollars. I'm going to give you $1 million. Do you mind that you're giving me the $1,000 now? No. Right? So $1,000 could be a large amount of money, but almost surely you need to do compared to what? If I'm giving you $1 million, you don't mind giving me $1,000 back. I think everybody would take that deal. If not, I strongly recommend you take some classes in economics or the business school. Right? This is as close to a no-brainer as you can get. So if my number's of size 10 to the 200, okay, 10 to the 200 is large, but it's minuscule relative to 10 to the 200 squared, which is of size 10 to the 400. So when we're looking at the cost of things, the cost of addition is so cheap relative to multiplication, we don't really care about it. I only care about the cost of multiplication. Okay, so we said that if we try to just evaluate this polynomial directly, the number of multiplications is going to be on the order of D squared. The number of additions is going to be on the order of D. So this, if my number is of size 10 to the 200, if that's the degree, this is going to be painful. It turns out that there's a nice way to evaluate things. I will prove it by just looking at the specific function I gave you. And this would be a good way to use some of the properties you have seen in mathematics. All right, so here's my function. Here's a better way to evaluate it. 7x minus 13 times x plus 11 times x minus 8, running out of colors, plus 12. I've just grouped things with parentheses. If you look at what's going on, this, 7x hits this x, then hits this x. Oops, I dropped the x here. Then hits this x, and that's going to give me a 7x to the fourth term. If I look at the 13, that's going to hit this x, then it's going to hit this x when I expand, then it's going to hit this x. That's going to give me a minus 13x cubed. If you look at this, when I expand this out, it's the same as the polynomial. From a theoretical point of view, does it matter how I evaluate the polynomial? If I'm doing just pure math theory? No. But in terms of practice, we just showed that this costs 10 multiplications if I do it naively. How many multiplications does it cost with parentheses like this? How many multiplications? 4. Cost is 4 multiplications, or D in general. So rather than have polynomial evaluation cost D squared, we can make it cost D by grouping the calculations in a more efficient manner. This is a great use of which properties from elementary algebra? What rule am I using? Who remembers the name? I'm going to write this out like this. What rule am I using? Begins with a D.
Distributed.
Distributive. This is the distributive law, right? It's not commutative. It's not the associative. I'm not switching orders. This is the distributive law. 7x minus 13 times x is 7x squared minus 13x. This is a great application of the distributive law. And so what we showed is that naively, a polynomial of degree d costs on the order of d squared multiplications. Using Horner costs on the order of d multiplications. That's a great improvement. But if I go from needing to do 10 to the 400 operations to needing to do 10 to the 200 operations, I'm still screwed. If the polynomial is special of the form x to the d, costs about 2 log base 2 of d multiplications. And this is a really good general rule that often can do better in special cases. So the first thing we did, the naive rule was order d squared. By being a little bit clever by using Horner's algorithm, we got it down to order d, which is great. But it's not good enough for our applications to RSA. We need something that's much faster. Something of size 10 to the 200 is useless. And so one of the reasons why this was not great is because we were trying to come up with an algorithm to evaluate any polynomial. And if we have to do any polynomial, we can't really exploit anything about it. And so the hope is that if we do a very specific polynomial, something with additional structure, maybe we can exploit that structure and do better. So the general case is going to be hard, but maybe a specific case is easy. Has anybody here taken probability? So you've seen central limit theorem? Have you seen Chebyshev's inequalities, that the probability that you release k standard deviations from the mean is at most 1 over k squared? So the larger k is, the less likely it is. If you try to use this with the standard normal, the probability that you're 10 standard deviations away from the mean in the standard normal is at most 1%. That's correct, but the number is so much smaller than 1%, it's laughable. Even 3 standard deviations is very small. The reason you have such a difference is Chebyshev's result works for any distribution that has finite mean, finite variance. It's not going to be as good of a result as the central limit theorem, where if you have additional structure, you can have more that's going on. This is hopefully just some phenomenon you've seen before. If you want something to be true in general, it's almost surely not going to be as good as something where you can tailor and use properties of what you care about. So this helps show why we've been doing some of the stuff we've been doing in group theory. We're beginning to see now, we had done RSA on the first day of class. We needed to compute various things. We needed to compute things to high powers. We've just seen how to do that in a reasonable amount of time. There's more stuff that we need to be able to do. We need to find, if I give you this integer e, you got to find this integer d such that e times d was equal to 1. We haven't seen how to do that yet, but we will. Okay, so now we're going to shift to the next part. We're going to shift to rings. And the idea here is we want to generalize integers. We want to look at objects that have 2 operations. And since we're generalizing integers, what do you think we're normally going to call those operations? Addition and multiplication. And of course, we say addition first. So we want to find objects that have addition and multiplication. You have all seen an example of a ring in one of the classes you've taken. but they have almost surely not used the word ring. And it's a class I've asked if you've taken today. So it's, I think, two possibilities, probability or linear algebra. So can you think of something from either probability or linear algebra where you might be able to have two operations? Matrices. Matrices. I want to be able to add and multiply. So I want to be able to multiply matrices. What kind of matrices must they be? Yeah, so they need to be square matrices. So if I give you A and B, I can easily do A plus B. If I give you A and B, I can do A times B. This is square. And so I could look at, we'll do it, you know, n by n of R would be all n by n matrices with real entries. And I can add any two objects, I can multiply any two objects. So integers have a lot of nice properties. And it's reasonable to ask, if I look at generalizations of the integers, if I look at generalizations of the real numbers, do those properties generalize? If I want to get back to real numbers, what should I take n to be? You know, can I view the real numbers as a special type of matrix? So I'm looking at n by n matrices. What would be a good value to take for n? By 1. So if n equals 1, you get the real numbers. If instead of looking at matrices with real entries, I want to look at matrices with integer entries, I would just say, okay, I want my entries not to be in R, but to be in Z, to be in the integers. So these are clearly going to be a generalization of the integers, or a generalization of the real numbers. So it's always good to try to put things in context. Is this truly generalizing something we've seen before? Yes. It's just generalizing integers, generalizing real numbers. And then you can ask which properties of the integers or the reals will survive when we generalize. So we just used the distributive law a few moments ago. Will the distributive law still hold? What's a really nice property the integers have with multiplication? And we've used this a few times.
They're commutative.
They're commutative. Will that hold with matrices? No. So unfortunately, some properties of the integers will not be kept as we go up to rings, as we go up to n by n matrices. So it becomes a question of which ones will be kept and why. So we have a long definition. Okay, definition 3.1. A ring is a set with two operations, generally called addition and multiplication. And we use the plus sign for addition, and we use either a dot or we just don't even write anything. We just put the two quantities next to each other, and it's multiplication implied. And we want the following axioms to be true. So why do you think we're using R for ring? Starts with R, right? So whenever you see a set beginning with R, almost surely it's a ring, but we still have to be explicit and say it is a ring. So the set R with its addition law plus is an abelian group. The identity element is denoted by either 0 or 0 with the subscript R. So we are insisting that addition is commutative. The set R with its multiplication law is almost a group, but its elements are not required to have inverses. Why do you think it's important that not every element has to have an inverse? What could be the issue? Can you think of any element that might have problems with having an inverse? Zero, right? The only thing we know is there has to be an identity, an additive identity element 0. And so we would need 0 to have a inverse. Could 0 have a multiplicative inverse? And again, you can be a smartass if you want. Can you give me a ring where 0 would have an inverse? So it's got to be an additive group under addition. What's the simplest group you can think of? What element do you know has to be in the group? The identity, 0. What if we only had 0? And you define 0 plus 0 as 0? How should you define 0 times 0? 0. Would that be an additive group? Yeah. Everything's going to have an additive inverse. Everything's going to have, we just define addition and multiplication to always give back 0. Would you have an inverse? Yeah. The inverse of 0 is 0. This is a really stupid set to look at. It's a set of just one element. So in general, as soon as we have two elements, then the additive identity is not going to be the same as the multiplicative identity. We're not going to be able to invert elements like 0. So we do not expect every element to be invertible. But maybe we're lucky and 0 is the only element that can't be inverted. Maybe everything else has an inverse. Maybe that's not the case. Maybe there will be multiple elements that don't have inverses. All we're saying here is under the multiplication law, it's almost a group. Its elements are not required to have inverses. So what must be true if it's almost a group, and I'm saying its elements don't have to have inverses? What must still be true? Under multiplication, what must be true? Yes. There's an identity. So we have an identity. And that's listed below. What else? Some of it's listed on the board. Associative. And there's one other thing. Closure. So a lot of times people don't explicitly list closure. I like to explicitly list closure. So when you say the set R with its multiplication law, implicit in that is closure. Is that if you take two elements in R and multiply them, you get back something in R. It's good to just be explicit and write that down. So we are assuming that it has an identity element, and we're going to denote that the multiplicative identity element as 1 sub R. So 1 sub R times A is A times 1 sub R is A for any A in R. A lot of times we'll just write 1 rather than 1 sub R. The associative law holds. We want the distributive law to hold. So earlier today, we saw how valuable the distributive law was. It's almost like I prepared a lecture, right? So A times B plus C is A times B plus A times C, and similarly on the other side. It's very useful to have something like this. So whenever you see definitions in your mind, you should be thinking about specific examples that you have. So you should be thinking about maybe the real numbers. You should be thinking about maybe matrices. Do these things seem to hold?
So if, when it says the set R with addition law in the abelian group, that means A plus B equals B plus A.
Correct, correct. So A plus B equals B plus A, but A times B is not necessarily B times A. And so if you think about matrices, then yes, they're going to be commutative under addition, but not necessarily under multiplication. And then if it turns out that multiplication is commutative, then in a shocker, we say the ring is commutative. And so we can easily see that if I look at 2 by 2 matrices, it's definitely not a commutative ring. It may not even be a ring. We haven't shown that it's a ring, but it's clearly not a commutative ring because we know examples of 2 by 2 matrices that don't commute. So now, if I give you, various sets, you need to go through and check all of these. Okay. If I give you an element and I ask for its inverse, what am I thinking of? So I have two operations. If I say I want its inverse, what inverse am I thinking of? Is there anything else I could be thinking of? I could be thinking of the additive inverse. What else could I be thinking of? Multiplicative. Not every element is going to have a multiplicative inverse. And then we might want to know what's the relation between a bunch of these quantities. So the first is proposition 3.2. So I'm not going to write everything on the board. I'm going to just highlight the key arguments in the book, because this is very similar to a lot of the proofs we saw on groups, and that's why we spent so much time on them. So let R be a ring. Then the first thing is 0 times A equals 0 for all A and R. When you look at 0 sub R is what element? So what do we say 0 sub R is? It's the additive identity. So the additive identity, if I multiply anything by it, I get 0. And the next one is basically what you would say is, oh, no, of course it has to be true. If I take negative A and I multiply by negative B, it's the same as multiplying A and B. What does negative A mean? What do we mean by negative A? We mean the additive inverse. So this is the additive inverse of A. So the additive inverse of A times the additive inverse of B is equal to A times B. In particular, we have negative 1 R times A equals negative A. And the way you should read that is, if we take the identity element under multiplication and look at its additive inverse, then if we multiply anything by that, we get the additive inverse of that. So if you multiply A by negative 1R, you get the additive inverse of A. All right, so the proof is pretty standard. We start with 1R equals 1R plus 0R. So rather than constantly saying R, I'm going to just say 1 and 0. The ring is understood here. Okay, so we start with 1 equals 1 plus 0. Why is this true? It's true because 0 is the additive identity. And so again, when we're trying to prove things, is what do we have in play? We know we have the identity elements 1 and 0. Okay, so 1 is equal to 1 plus 0. So I now take A and I multiply it by 1. But that's the same as multiplying it by 1 plus 0. So another way of looking at it is, we start off with A equals A, and on one side we multiplied by 1, and on the other side we multiplied by 1 plus 0. We're doing the same thing to both sides. And now we use the distributive property, so we can see immediately that this is going to be of use, and we get A times 1 plus A times 0. And we know, since 1 is the multiplicative identity, A times 1 is just A. So we get A equals A plus A times 0R. You would love to say it this way. Well, clearly, then A times 0 is just going to be 0. But that's what we're trying to prove. But we have A on both sides, so let's add the additive identity of A to both sides. So negative A plus A, the additive identity of A plus A is just 0. But we just showed A is A plus A times 0. And now we use associativity. We regroup things, and this is something we've done all the time when we're doing things in group theory, so that the additive inverse of A, negative A, is right next to A. And then that's going to be 0 plus A times 0. Well, since 0 is the additive identity, anything plus 0 is itself, so we get A times 0. And so finally, when the dust settles, we get we get 0 equals A times 0. Okay, so multiplying by 0 gives 0. This was not a foregone conclusion. 0 was the additive identity. And it turns out that the additive identity is functioning the way you would hope it would be. This is good notation to call it 0, Because now when we think about multiplication, your thought should be, if I multiply anything by 0, I should get back 0. But I could have written the additive identity differently. Instead of using the 0, because I know how things are going. Right. So I'm not going to go through the second part. I'm going to leave that for you, is you should try to do part B. So try to do B. And try to mimic what was going on in the proof of part A. Try to think, which items should we look at? How should we combine things? If I want to talk about minus A, I know minus A plus A is 0. So that's a good thing to look at. Sometimes it's easier to break problems up into smaller things. Rather than proving maybe minus A times minus B is this, maybe you just do first with one minus sign. So maybe do an easier problem. So maybe do minus A times B equals minus AB first. And of course, A times minus B equals minus AB. The other thing is, maybe prove useful results. What do you think minus minus A should be? A. Is that trivial? How would you read it?
The inverse of the inverse.
Which inverse? You have to be very explicit.
The additive inverse of the additive.
The additive inverse of the additive inverse of A is A. Does that seem very reasonable? Yeah, that shouldn't be too bad. So when you say it out loud, the proof almost writes itself. The additive inverse of the additive inverse. Yeah. This is very similar to in group theory. The inverse of the inverse is the element. Yes. Think. What is the tangent of the arctangent of X? What is the tangent of the angle whose tangent is X? X, right? So for some of these things, if you just say them out loud. So, again, when you're trying to prove something like this, do you want to try to prove it directly? Do you want to try to prove minus A times minus B is AB? Or do you want to try to prove some simpler things first? That the additive inverse of the additive inverse is itself. So maybe I just pull out the two minus signs. I pull them out one at a time. And that's what I'm trying to do over here, is say, minus A times B is minus quantity AB. And I've just pulled out a minus sign. And so if I can keep doing that, so this might be breaking up a complicated thing into a bunch of simpler things. This might be a bad way to do the problem. My feeling is that this is a good way to do it. You break up something complicated into a lot of simpler steps. And of course, when you're done, you will then also have other results that will be of use. That minus minus A is just A. Okay. So a lot of what we're going to do now is take what we've done for groups and try to generalize it to rings. So if we have two rings R and R prime, a ring homomorphism from R to R prime is a function phi satisfying the following properties. Phi of the additive identity is the additive identity, but additive identity R goes to the additive identity in R prime. This is where it's useful to now include the subscripts of what ring are we talking about. If I write just 1, it's not necessarily clear, am I talking about 1 in the ring R or 1 in the ring R prime? Phi of A plus B is phi of A plus phi of B. Phi of A times B is phi of A times phi of B. What does this look a lot like? Where have you seen something that looks a lot like this before? Yeah, for the groups. It looks like a lot like a group homomorphism. But because we have two operations, we have to have two things for phi. We have to have phi is like a group homomorphism for addition, and it's like a group homomorphism for multiplication. We have an additional property. What's the additional property? So we have something here that we did not have when we defined a group homomorphism. We have something in this definition that was actually a theorem when we looked at group homomorphisms. Yeah, phi of 1R goes to 1R prime, that the identity of R goes to R prime, R prime's identity. So the question is, do we need this? Is this needed, or does this follow from the other stuff? Sometimes we have definitions that are not the weakest that we could do. Sometimes these definitions just make life easier for us. How many of you have done calculus? I mean, this is who's awake right now, right? This is a prerequisite for the class. You've all done calculus. So you have the fundamental theorem of calculus. The area under the curve y equals f of x is the antiderivative at b minus the antiderivative at a. You do not need your function to be continuously differentiable. You can use some results from analysis. Who here has taken real analysis? Okay, so if you take real analysis, you have some powerful techniques that you can use, and you do not need your function to be differentiable. If you haven't taken real analysis, it's going to be a little bit hard to show that the upper and the lower sums converge to a common value. If the function is differentiable, you can use the mean value theorem and everything falls. Most of the time, if you're teaching Calc 1, Calc 2, Calc 3, the functions you're looking at are continuously differentiable. It's not a severe restriction to put in, I'm going to just assume for convenience that my function is differentiable. All the situations that are going to come up in the classes I'm looking at, the functions are going to be differentiable. I'm not going to bother proving things in the greatest possible generality. And then when you take a class like probability, you have these nice probability densities that are continuous and differentiable. None of this is a big deal. But it's not needed. You don't need your function to be continuously differentiable for the fundamental theorem of calculus to work. If the function is continuous, that's enough. Piecewise continuous is enough. And you can get into a game, what's the weakest set of conditions you can do? So I'll leave this as something for you to ponder. Do we really need to assume that the additive identity is sent to the additive identity, or does it just make life easy that I no longer have to worry about proving that? Any function I'm looking at, I'm going to just have that to work with. So, I'm sorry, multiplicative identity. Sorry, thank you. The multiplicative identity is sent to the multiplicative identity. Thank you. So the question is, do we really need to include that as part of our definition of a ring homomorphism, or does that just make life easier? I mentioned that one of the things I could give you for group theory is if you have a left inverse and a left identity, that implies that the left identity is also a right identity and the left inverse is also a right inverse. It's not necessarily fun to prove. And so most of the time, let's just assume we have a two-sided identity, and let's assume if you're an inverse on both sides. In all of the situations we're looking at, that's true. So let's make our lives a little bit easier. Okay, so the kernel of phi is the set of all elements that are sent to 0, that are sent to the additive identity. So kernel of phi is all A and R such that phi of A goes to 0. Now you're going to be very careful as to which 0. So this over here, really, let's call that 0 R prime. Because there are two zeros at play. So we have a ring over here, R. We have a new ring over here, R prime. And we have some map phi between them. And we're saying that the identity element 1R goes to 1R prime over here. And then the kernel is all things that are going to be sent to the additive identity. As with groups, we say R and R prime are isomorphic if there's a bijection, so 1-to-1 and onto homomorphism phi from R to R prime. So where does the kernel of phi live? Does it live in R or R prime? So the kernel of phi lives in which? R, R prime? R, right? It's the set of all elements A and R that are sent to 0. what might you ask about the kernel of phi? It lives in R. So think back to what we did in groups. When we did groups, we had phi was our group homomorphism, and we looked at the kernel of phi, all the things that were sent to the identity. Did we prove anything about the kernel of phi?
Is it isomorphic or something if it's contained only one element?
Good. So if it has only one element, they gave us some information about. But what about just the kernel of phi itself? What about all the elements in the kernel of phi? We have a group. We have a subset in the group. What could you ask about that subset? Is it a subgroup? And so what do you think you could ask here? We have the kernel of phi lives in R. Is the kernel of phi a what? A subring. Does everybody agree asking is the kernel of phi a subring is a natural question? What have I not defined in this sentence? Subring, right? Oh, so you're asking the question, you're making the conjecture without even defining what a subring is. Excellent, right? We had groups and subgroups, so clearly we should have rings and subrings. And so the definition hopefully suggests itself. A group, we take a subset of that, and then we want that subset to be a group with the same composition laws as the original group, just it's restricted. So a subring should just be something that lives inside R and is a ring with the same composition laws. So we need addition and multiplication to be closed in the subring. If I take two things, they stay. What should we be thinking of from linear algebra as a motivation? Subspaces. And so we'll need the identity elements to survive. A lot of the properties will just be inherited. As long as we have closure, well, we have, oops, sorry, I went back to the wrong slide. Sorry, wrong slide. I just saw lots of text. So if we assume we have the two identity elements, we don't have to really worry about associativity because we get associativity because they live inside R. R is associative, and a subset is associative. The big thing is we need closure. We also need, for the addition law, everything has an inverse under addition, but that may not be in the subring. Or it may not be in the subset. So if we want the subset to be a subring, we know any element has an additive inverse, but that additive inverse may not be in our subset. That has to be true if we want it to be a subring. It was just the same as we had the subset with the group. We know every element has an inverse because it's a group, but that element doesn't necessarily have to live in the set. So it's a very natural question to ask, is this a subring? And I will leave that to you to think about. All right, so interesting examples of rings. So let's define the ring Z mod MZ, which we've seen before, to be the set of congruence classes. So for example, if I give you m equals 12, I can define Z mod MZ as 0 plus, I guess I'm using 12, as 0 plus 12Z, 1 plus 12Z, ... 11 plus 12Z. And if I take, say, 7 plus 12Z and 9 plus 12Z, what would that equal? So what would 7 plus 12Z here? A plus 12Z is going to be all numbers x of the form A plus 12K with some So a plus 12z is going to be all the numbers whose remainder is a when I divide by 12. So all numbers of the form a plus 12z. So if I have 7 plus 12z and I add 9 plus 12z, what should I get? Four plus 12z. Or what else could I get? So 4 plus 12z is correct. What else could I get? If you don't do your simplification, what would you get? You must have reduced something to get 16 plus 12z. And let's think about what's going on. 16 plus 12z is all numbers of the form 16 plus 12k. K is an integer. What about 4 plus 12z? What's that? That's all numbers of the form 4 plus 12l. L is an integer. Are these two sets the same? Are the set of numbers of the form 16 plus 12k the same as the numbers of the form 4 plus 12l? Yeah, I mean, if you look at the first one, when k equals 0, what do you get? 16. When k equals 1, what do you get? 28. If k equals -1, you get 4. If k equals -2, you get -8. All right, is that right? Yes. Whereas if I look over here, the 4 plus 12l, if L equals 0, what do I get? I get 4. If L equals 1, what do I get? 16. If L equals 2, I get 28, ... If L equals -1, I would get -8. These two sets are the same. If I look at all numbers of the form 16 plus 12k, and I look at all numbers of the form 4 plus 12l, they're the same numbers. Right? I've just written them differently. How could I go from one to the other? Can you give me a map that takes something from 16 plus 12z and gives me something of the form 4 plus 12z?
Minus.
Yeah, I could do something like that. I could do, f of x is x minus 12. So frequently, there could be more than one way to have a representative of my set. So both 4 plus 12z and 16 plus 12z are the same. And we often use the 4 plus 12z because it has the smaller number. So if I look at these elements, 0 plus 12z, 1 plus 12z, all the way up to 11 plus 12z, if I want to add any of them, I'll define the addition as just take any element in one, add it to another. And you can see it's going to be all numbers of the form, 7 plus 9 plus a multiple of 12. Well, okay, that's 16 plus a multiple of 12. I can shift my multiple of 12 down by 1 and reduce the 16 down to 4. So really, when I want to add these elements, I can just add the 7 and the 9 and just reduce it. So in addition to adding two elements, what could I do next? I could multiply. Let me just add one page. What if we multiply? So what do you think? 7 plus 12z times, what was the other one? 9 plus 12z? What do you think that should equal? What would you guess? It doesn't have to be the most simplified answer. Give me an answer that you think should be fine. So I have. Okay, but okay, give me the easy one first before. So what do we think 7 plus 12z times 9 plus 12z should be? So you said 3. What were you doing to get to the 3? So we think this should be 63 plus 12z, which then becomes the same as 3 plus 12z. Because 63 is 60 plus 3, 60 is a multiple of 12. If you think about what's going on, if I take something in 7 plus 12z, that's something in the form 7 plus 12, let's call it k. And I'll take something here, that'll be the form 9 plus 12l. And if I multiply them out, what do I get? I get 7 times 9 plus 7 times 12l plus 12k times 9 plus 12k times 12l. That's 63 plus 12 times 7l plus k times 9 plus k times 12l. Ah, this is a multiple of 12. So this is basically equal to, if I wanted to, I could write this as 3 plus 12 times 5 plus 12 times 7l plus k9 plus k times 12l, or 3 plus 12, I'll bring in the 5, 5 plus 7l plus k9 plus k times 12l. And then you just do a little bit of work just so that you can get anything you want. Now, these sets really are the same. Do you think every element is going to have an additive inverse? You look at V mod 12z, that's going to be 0 plus 12z, 1 plus 12z, 11. We see that this is correct. We need the additive inverse, the additive identity, and the multiplicative identity. What do you think they should be? 12 elements, 0 plus 12z, 1 plus 12z, 2 plus 12z, all the way up to 11 plus 12z. What do you think the additive identity should be? 0. Multiplicative identity should be 1 plus 12z. You think every element is going to have a multiplicative inverse? So can you give me an element from 0 plus 12z through 11 plus 12z that probably does not have an inverse? And there should be natural candidates to search. 4. Why did you choose 4? Okay. And why is 2 bad?
Because it's not really good.
It's not relatively prime to 12. So maybe the issues in a multiplicative inverse, a plus 12z if GCD of a and 12 is greater than 1. So if I give you a number that has a common factor with 12, maybe I could have trouble in having the example. Let's say I want to do 4 plus 12z times x plus 12z equals 1 plus 12z. Okay, I'll let you go through and show that 1 plus 12z really does act as the multiplicative identity. That's not just too bad because we said the way you multiply them is you just multiply the whatever's in front of the plus sign. And then it's, if you had 3 plus 12z and 5 plus 12z, it's 3 times 5 plus 12z. If I give you a plus 12z and b plus 12z, when you multiply them, it's a times b plus 12z. So if I choose 1 plus 12z, it's not going to be too bad to show that that really is the multiplicative identity because you're just multiplying by 1. If we wanted to solve this, then this over here is the same as 4x plus 12z equals 1 plus 12z. So we need to find an integer k such that 4x plus 12k equals 1 plus 12l for some l. So we need 1 to equal 4x plus 12k minus 12l, which is 4 times x plus 3k minus 3l. Is there any way to do that? Is there any way to find a choice of x, k, and l such that this equals 1? No. Why not? Right. Yeah, is a multiple of 4, and the left-hand side is just 1. So this could be a really good example of a ring. We have the addition, we have the multiplication, and multiplication, not every element is going to have a multiplicative inverse. So you can say, well, okay, we've already agreed that not every element has to have a multiplicative inverse. It's unreasonable to expect 0 to have a multiplicative inverse. But now we have numbers like 4 plus 12z that's not going to have a multiplicative inverse. So when we talked about what we want in the definition of a ring, we can't just say it's a ring if it's almost a group under multiplication. 0 is not required to have an inverse. Here's an example which is looking a lot like a ring. Everything is going nicely. We can define multiplication. We can define addition. We have the identity elements, but not every element that's non-zero will have a multiplicative inverse. If I gave you 5 plus 12z, could you find a multiplicative inverse for 5 plus 12z? Itself, right? This is very similar to the group 1, 5, 7, 11, which we've seen many, many times. Okay, another good example is the Gaussian integers. So it is a subring of the complex numbers. So has everybody seen the complex numbers? So I equals the square root of -1, or I squared plus 1, -1. So the Gaussian integers is going to be all numbers of the form a plus bi, where a, b are in C. So if I give you two numbers, a plus bi plus c plus di, what would that equal? How should we add two elements like this?
A plus C
A plus c, good.
plus B plus B bracket I.
Good. Now, what if I did multiplication? Let's just FOIL it out. And that would be AC plus BCI plus now we're going to do ADI plus BIDI. But what's BIDI?
Negative BD.
Negative BD, because we're going to have an I squared. So this is going to be AC plus BCI plus ADI minus BD. And then let's put all the real stuff together, AB minus BD plus BC plus AD I. And so we've now come up with a way to define addition and multiplication. And now we can just go through and check and see that this is a ring. And it turns out this ring has a lot of very useful properties in number theory. We've actually seen a little bit of this when we did the special lecture on Pythagorean square day 9, 16, 25. When we were talking about the circles and ways to combine numbers and why it actually stayed on the circle and generated new Pythagorean triples. This is what was lurking beneath. Do you think every number is going to have an inverse? Excellent. An additive inverse. Will we have additive inverses? Yeah, it would just be negative A minus BI. But multiplicative inverses, very few numbers will have multiplicative inverses.
What's the multiplicative identity?
So what do you think the multiplicative identity would be? So additive identity is 0 plus 0i. Multiplicative identity, what do you think?
1 plus 0.
1 plus 0i. And so that would be the multiplicative identity. And so if you look at things, it's going to be pretty hard to find multiplicative identity. So if we want A plus BI times C plus DI to equal 1, which A and B is there a chance of being able to have an inverse? So hopefully you've seen the following. If I give you some complex number Z, the absolute value of Z squared is Z times the complex conjugate of Z is X squared plus Y squared if Z is X plus IY. Does this look familiar? So if I give you some complex number, its length squared is itself times its complex conjugate. And the length squared of ZW is the length of Z squared times the length of W squared. And we saw that a little bit on 916. Well, if we use that, over here, then we would get the length A plus BI squared times the length of C plus DI squared equals 1, with A, B, C, and D integers. If A, B, C, and D are integers, we need two numbers that multiply to 1 that are forming from where's the integers? So what must be true about each of these magnitudes? What's the only possibility for A squared plus B squared? 1. And what's the only possibility for C squared plus D squared? 1. So we need A squared plus B squared equal 1 to have a chance at being invertible. And A and B have to be integers. So what are the only possibilities for A and B if I want A squared plus B squared equals 1? What are my only chances? Could one of A or B equal 2? Negative 2. No. So the most any of these can be is 1. Could both of them be 1 or minus 1? No. So one of them is plus or minus 1, and the other is 0. So my only possibilities are going to be 1, minus 1, I, and minus I. Those are the only numbers that have a chance of having a multiplicative inverse. It turns out they all do have a multiplicative inverse. But in general, most numbers are not going to have multiplicative inverses. You can also have polynomial rings. And so what we can do is we can look at a polynomial of degree D, which we've done several times today. But if I take a polynomial of degree D and I multiply it by a polynomial of degree D, what's the degree? Not D squared. Polynomial of degree 5 times a polynomial of degree 5 is a polynomial of degree x to the 5th times x to the 5th is x to the 10th. It's 2D. So if I just looked at polynomials of degree D, if I multiplied, it wouldn't be closed. So we have to look at polynomials of finite degrees. So these are going to be polynomials of finite degree. As you know, degree D times degree D is going to be degree 2D. There's only one choice of D where D and 2D are the same. What's the one choice when D and 2D are the same? 0. And so if I have degree 0, then my polynomials are just constants and it's just not real numbers again. So the real numbers would be a very special case of polynomials. They would be the degree 0 polynomials, and they would be closed under multiplication. A real number times a real number is a real number. But if I give you a degree 1 polynomial times a degree 1 polynomial, in general, that's going to be a degree 2 polynomial. So when I look at it, I have to look at polynomials of finite degree. So my set is going to be all polynomials of finite degree, and then it's an exercise to show that this is a ring. So again, I'm not requiring you to do a tremendous amount of homework. The more problems you do, the more likely it is things are going to sink in. So if you feel comfortable that, yes, if my life depended on it, I could go through and verify all the properties, that's great. I'm not going to require you to write this up and hand this in. But you should make sure that you are comfortable going through and showing that this does satisfy the requirements of a ring. You should be able to find what is the additive identity, what is the multiplicative identity. Perfect. Then there's the evaluation map, which we actually talked about a little bit earlier. It's a ring homomorphism. And what it does is you take a polynomial and you evaluate the polynomial at C. And again, this is just going through and unwinding the definition. So again, you should make sure that you are comfortable doing something like that. Okay? So again, there's a lot of things to check. A lot of these calculations are very similar. You're going to see them again and again and again. And so once you master them, you can then apply them in a lot of different settings. The whole point is to try to break up complicated objects into simpler objects that are going to be easier to study. And then you can always ask, of course, who cares about these objects? And so there's lots of applications. I like Rubik's Cubes. You know, solving Rubik's Cubes is a fun application of group theory. It's one of the more interesting groups you can come up with. But, you know, as somebody who was trained in number theory, who lives in the 21st century, encryption, data transmission, this has to be the central problem that we care about. And we need to be able to do things securely. We need to be able to do things quickly and efficiently. So we've got 2 minutes left. And so I will end with the following. In RSA, we kept secret times P, Q, and E. We made public N, which was P times Q, and D with E times D congruent to 1 mod P minus 1, Q minus 1. And then if we want to message M, we send M to the E mod N, and you decrypt by doing M to the E mod N to the D mod N. When we're doing, raising M to the E, if E is of size 10 to the 400, we showed that that's not bad. We showed with fast exponentiation, we can do that. And the mod N, you don't have to do all of the multiplication and then do mod N at the very end. You can keep doing mod N every single time to keep things small. So you want to show like, M mod n times m mod n is the same as m squared mod n. You can reduce and then multiply. So the only thing that's left is we need to be able to find large primes. And we need to be able to find a d such that ED equals 1 mod p minus 1 q minus 1. So the question is, and I'm not going to answer it for you now, but think about it. Do we know how to find such a d? Have we done anything so far this semester that would allow us to figure out what that is? Good place to stop.